half an hour. We're doing 8.1.
Does this mean you're going to talk really fast?
I can option here.
Can you put the video on
I
slow
can't
motion?
talk very fast. We're going to start our discussion with sequences.
That's why we tape it, so we can rewind.
Yeah.
Because really, series are just adding the terms of a sequence. You can sort of think of it that way. So let's start with sequences. So I said here, do an intro talking about the Fibonacci sequence, but we're going to skip that, of course. Because everyone knows about the Fibonacci sequence. If you don't,
Of course, if you don't read the stock market. If you don't, go look at rabbits. Observe rabbits. Observe rabbits and do really well in the stock market after observing them.
No,
Yeah, by the way, what are my stocks doing today?
Alright, that's it. Sequence is just a list of numbers, right? That are ordered in a certain way, which I'm going to talk about the order pretty soon. Each number in the sequence is called a term. We can say the first term of the sequence, the second term of the sequence, the third term of the sequence, etc. It's just talking about a certain element. And notation. Is usually lowercase letters. With subscripts. So for example, I can call the sequence A, where n ranges from 0 to infinity, by saying A1, A2, A3, A4, etc. Right? So this is the first term, second term, etc. Right, so it's just some list of numbers that follow some definite order. Usually we will be able to follow it by some mathematical formula.
Does it start from n equal from A0?
Should be A0. 1, 2. Right, so this notation actually tells you where the starting subscript is. So we're numbering elements starting with 0 and continuing to number them to infinity. We can think of this function whose inputs are the non-negative integers So if you see something like an, you think of it as the function a evaluated at the number n, and it gives you some output. Right? So you can think of it that way. Yes. So you can think of it as a function from the integers to the set of real numbers. That's another way to think of sequences.
So could this be something calculated iteratively, where the value of a sub 2 depends on a sub 1?
Yes, both are possible. And you can have one given by, right, when you say it's completed iteratively, you call those recursive sequences. And you have sequences that are computed by some definite formula that you can write down, you call those closed form sequences. And any other sequence is just a sequence. Okay, so example, I can have the sequence an equals 1 over n. Right? So I'm defining the terms of my sequence, or let me write it as n goes from 1 to infinity, defined by an equals 1 over n. In which case I'm saying the list is the list. What's the list? Well, I'm starting at n1. The a1 term would just mean I plug in n equals 1 into this formula. Right? So this is just a1 would be 1 over 1. a2 would be 1 over 2. a3 would be 1 over 3. a4 would be 1 over 4, etc. Right? So this sequence is just the list 1, a half, a third, a fourth, so on, right? So it's a list of numbers. They have some definite order that I can find from a mathematical formula or some other obvious pattern. Right? So that's an example of a sequence. Or you can literally put the formula inside the bracket. So I could say something like ln of n goes from 1 to infinity. That's just the sequence ln1, ln2, ln3, ln4, etc. Right? So your variable is usually assumed to be an integer. Right? That's how we're defining it. Right?
Professor?
Yes.
Is it supposed to be 1 or n?
ln n. Right. So when n is 1, I plug in 1. When n is 2, I plug in 2. When n is 3, I plug in 3 into this formula. And I'm creating the list this way. Right? So this is my list where the first term is ln of 1, which is 0. The second term is ln2. Third term is ln3, and so on and so forth. Right? So sequence is just a list of numbers. Right? That's how we're looking at it. Okay. Sometimes, assuming a mathematical formula is behind the sequence, you need to figure out the formula. Example. Try to figure out a formula for that sequence. Yeah?
1 plus n times negative n over 2n plus 1.
You said an is equal to what?
1 plus n over 2n plus 1 times n.
Which part is over? The whole thing over?
2n plus 1 times n minus.
Maybe negative 1 to the n?
No, not
Negative
negative
1?
Negative 1 to the n. Everything to the
No,
n.
negative 1 to
Okay, and n starting from what? So does that actually work? When n equals 0, Notice that when n is even, you get this to be a positive 1, so it doesn't change the value. But when n is odd, you get it to be a negative 1. Right? So this would be the 0 term, give me a positive 1. The first term that gives me a negative 1, positive 1, negative 1, positive 1, negative 1. This is actually a very good way to alternate the sign. It's like something we're going to see all the time from now on. Minus 1 to the n. Right? It's a way to alternate signs. Right? So this alternates every 1, so this should be minus 1 to the n. Notice that when you start at n equals 0, this is 1. 2n plus 1 is a generic term for an odd integer. Notice that the denominators, if you look at this as 1 over 1, are all odd integers. 1, 3, 5, 7, 9, etc. Right? So 2n plus 1 was a very nice formula to use. Right? Notice that when n is 0, you get 1. When n is 1, you get 3. When n is 2, you get 5. When n is 4, you get etc. Right? You get all the odd numbers. And then this just starts at 1 and then keeps counting up. 1, 2, 3, 4, 5. So that's a good way. I could also make this n and then change this to n minus 1 or anything similar can work. So that's one formula. So those they ask you about all the time, about trying to come up with a formula that solves some pattern of numbers. Because a lot of mathematics is about figuring out a pattern to something and then using that to solve a problem. So sequences are things that show up all the time that we'd often like to find a pattern for and to be able to solve problems with. One of the things we care a lot about is whether a sequence converges. Now let me define what converges means. I think I put a let me see what's converges just means it has some limit. If you take the limit of the terms of the sequence, you can make the points in your sequence get close to some value by making your n large enough. Arbitrarily close just means within whatever distance you desire. Example. Sequence one over n, and goes from 1 to infinity, converges to 0. How do I know it converges to 0? Well, let's see if I actually plot these guys on a number line, n versus an. Right? The first term for n equals 1 would give me a point plotted at 1. Right? N equals 2, I would get a half. N equals 3 would give me a third. N equals 4 would give me a fourth. N equals 5 would give me a fifth. Notice that all these terms are getting super close to 0. right? If I want to be a distance 1 away from 0, I just pick n equals 1. What if I want to be within a third away from 0? Just pick n equals 3 or bigger, right? So I can actually get as close to 0 as I want by making n big enough, right? And what that means is that all your points sort of settle somewhere, right? Essentially this means the limit exists and it equals some number. Right? It's essentially the same as taking the limit as n goes to infinity of the formula. So figuring out if a sequence converges or not, all you have to do is find the limit of the terms. If they go to a number, you say converges to that number. There's also the notion that a sequence can converge to infinity. Actually, this basically means a sequence converges to infinity if no matter what positive number I pick, eventually the terms of my sequence will exceed that number, no matter which number I pick. Right? So example, look at the sequence an from 1 to infinity, where an is just equal to n. Right? Then this sequence converges to infinity because that limit is infinity. So it means no matter what positive number you tell me, 15, eventually the terms of my sequence will pass 15, right? Just take little n to be 15 or bigger, right? 25, eventually the terms get bigger than 25. 1,000, eventually they'll get bigger than 1,000. 1,000,000, eventually they get bigger than 1,000,000. No matter what positive number you call, eventually these numbers will exceed that. Whenever that happens, you say the sequence converges to infinity. If no L exists, then the sequence is said to diverge. Example. Sin n actually never settles anywhere, right? It keeps oscillating, right? There'll never be a number where you can say, you can make it arbitrarily close to that number, because it will always start to bounce up and down, right? So because your sine is going to follow a certain pattern, that will never settle anywhere, right? So you can't say the limit is 0 because once you get within some small window of 0, your sequence will jump out of that window. Right? So this sequence limit does not exist, and so you say the sequence an equals sine n diverges. So it's nice if you have a pattern of numbers that actually tend towards some other number, you say it converges, right? If it always gets bigger and bigger and bigger and bigger, you can say it converges to infinity. Some textbooks actually call infinity divergent. We'll actually adopt that, because I think most textbooks actually think of it that way. We shall say an converges if L is finite and diverges otherwise. But I'd like you to specify when it diverges to infinity in particular, or just you can't put a handle on it one way or the other. And just in case you were wondering, let me actually just say. That's sort of the summary. Right? Want to figure out some of the conversions, take the limit, and all the limit rules apply. Right? So this implies you have certain properties. Limits split across sums, therefore to find out if the sum of two sequences converge, you can just find out if each individually converge and add them together. And if I don't write it, it's always to infinity, right? There's no other number to take a limit to for a sequence. Right? Always assume infinity for sequences. That's the only limit that matters or even makes sense. If I take the limit of a constant times the sequence, is just equal to the constant times the limit of the sequence. Because you can factor constants outside of limits. All your limit rules still hold. If we have the limit an times bn, this is just the limit of an times the limit of bn. If we're taking the limit of an divided by bn, this is just equal to the limit of an over the limit of bn, provided the limit of bn is of course not equal to 0. 5, talk about the limit of an raised to some power is the same as taking the limit of an and raising it to that power. That works for positive sequences. The squeeze theorem also holds. I mean, your book probably proves all these, but we're not going to prove it. We're just going to assume them. Assume you remember the proofs from Calc 1. What else do we need to know? Let me specifically say what this means. If your an less than or equal to bn less than or equal to cn, and the limit of an is equal to the limit of cn equals to L, then limit of bn equals to L. That's actually a property we're going to use all the time. There's also another theorem. We're just listing facts that we're going to use all the time. Eventually we'll get to use them. If the limit of the terms in absolute value equal to 0, then it means that the limit of the original sequence equals 0. That's of course not true for any other number, only 0. I guess I'll stop there. The rest of it is just reeling off some facts about sequences. Just going to be a lot of boring note-taking anymore. We can do that tomorrow after the test. So stop there. I didn't finish this, and you wouldn't worry about the homework anyway because of the test tomorrow. Make sure you study for the test.